Good morning.
Good morning.
Thanks for getting up early and having a cup of coffee and a kolache. That's the reason I came. Kathy and I have been working together for 15 years, and collaborative effort of understanding reservoir architecture and its effect on fluid flow, and we'll run through some of that today and hopefully help you see some of the advantages of understanding a reservoir on a first principle scale to determine how flow works. We'll start off with a little quote here. George Box was one of the brilliant minds of statistics the last half of the 20th century. He was a Brit and learned to do statistics during World War II. And I always keep this quote in the back of my mind as I'm looking at things. All models are wrong, some models are useful. Well, why is that? Well, it turns out that a model is a visual or mathematical or physical representation of a real world phenomenon, but it is not the real world phenomena. Because of the infinite variations found in nature, models are imperfect representations of real world phenomena. Our goal should be, as scientists and engineers, is not to find the perfect model, but to find the useful model. And that's what we're going to talk about today, the things we can do to help do that. Well, how do we know how it works? Well, they're useful to the extent that they represent the physics and chemistry of the system. And this is true of both visual and of mathematical models as we look through these things. And the way we know that they're useful is they represent the first principles. Geology is important because it determines the physics and chemistry of the reservoir system. Fluid location and fluid flow in multi-phase systems are controlled by the physics and chemistry. I got started on this about 20 years ago. I drilled a series of wells, and every indication was they should have been very good oil discoveries, and yet most of them made very high water cuts to all water. I said, there's something here we don't quite understand. And like most people, I said, okay, I'll try and come at it from the engineering side. Well, I started on that and I looked around and said, you know, there are a lot of really smart engineers out there. And if there is an issue here, I probably am not going to do a better job than they are of understanding it from that standpoint. But I am a pretty good scientist. So let's start looking at the geology, let's look at the physics, let's look at the chemistry of the systems and see what we can figure out from the first principles to understand this type of flow in oil and gas reservoirs. It turns out that despite some of the cross plots we make when we're looking at reservoirs, for example, capillary injection pressure versus water saturations. Those are both dependent variables and not controlling variables. The things that really control fluid flow in a reservoir are the reservoir architecture. That's Kathy's forte, and she'll be talking about that to a large extent. Energy at the interface of the phases, the interfacial tension, that's the maximum energy in any flow system. So if you're going to change flow, you have to overcome the maximum energy to reestablish a minimum energy flow path. And finally, energy equilibrium. Almost all of what we do in oil and gas assumes that the reservoirs are at equilibrium when we drill in them. That's not just reservoir modeling, it's also our fluid selection on drilling and completions. The reason we use water is we think, well, if we're at equilibrium, the water goes in, the water comes out. But if we're not at equilibrium, there are some physical things that happen that prevent that from happening. And we'll show you some information on that also. So let's start off with some visual models here. This is a model of fluid flow that would put two phases in one pore network. And so we have a fluid location of two phases, one pore network, and the way we would have phase trapping in this is to disconnect one of the fluids, in this case the hydrocarbons, so it couldn't move a continuous phase through it. And the way we fix that phase block is to restore that continuity of the phase. Here's another model. This is with single phases being in different pore networks. And the way that we would flow one or the other is because the oil and gas is in the bigger pore network, it has less capillary forces holding it, and it would flow, and the water would not because it's in smaller pores, pore networks, and the capillary forces would hold it. The way phase trapping works in this system is that we imbibe another phase, in this case water, into the oil or hydrocarbon pore network, and it blocks it off. Now, if the interface in that pore system requires a higher delta P to get it out of there than the delta P required to get the water moving, all of a sudden I've turned an oil reservoir into a water flowing system. We'll talk a little bit more about that also. This is Standing's model. Standing worked for Chevron Oilfield Research, and his model is this. We start with a reservoir rock charged with water. And by the buoyancy force we get from the density difference between hydrocarbons and water, we start injecting hydrocarbons into the reservoir. The hydrocarbons go into the pore network that has the least capillary forces holding the water first. And the first thing that goes in is gas because it has a greater density difference. As time goes on and we build column, we can put the hydrocarbons in smaller and smaller and smaller pore networks. But in the end, the oil and gas are in the large pore network, and the water is in the smaller pore networks. Mobile water simply means it's a continuous phase, and if I have enough force, I can move it. Irreducible water means that it's a disconnected phase, and it will not move no matter how much force I put across it, because it has to be continuous to flow. Here's some work done by Norm Morrow, University of Wyoming. He was as he liked to refer to himself, a surface microsurface geochemist, and did some great work up there. And the point of this slide is that we do see the red, the non-wetting phase, completely fill a pore network, and we don't have a mixture of water and or non-wetting and wetting phases in a pore network. So we've displaced all the water out, and we have indications. The model that works is the model on, I guess, my right, your left as you're looking at it, not the model on the other side there. So as we charge hydrocarbon reservoirs, we sort the fluids out into different pore networks. And the oil and gas are in the big pore networks, and the water is left in the small pore networks. And that has some very telling implications as we start to look at relative perm and fluid flow and multi-phase flow in an oil and gas reservoir. Well, what are pore networks? They're composed of combinations of pores, pore throats, and fractures that have the same fluid entry pressure. There are a large number of pore networks in any reservoir rock, and so we sort the fluids into these different pore networks by their fluid entry pressure. Fluid or fluids will flow in the pore network or networks that require the minimum energy expenditure. So we will move the fluids through the pore networks that it's easiest to move it through. Part of a reservoir's energy is stored at the interface between the phases in a reservoir, and that is the interfacial tension. Pore throat size and shape control the shape of the meniscus and consequently the energy at the interface. So the energy, maximum energy in the reservoir that affects flow is at this interface between phases. And so we isolate off a pore network that has a single phase in it, but if we imbibe another phase into there, we can phase block that reservoir very quickly. We're going to look at some reservoir architecture now. I want to start off with the model. This is what the reservoir looks like in terms of how we derive the mathematical flow or formulas in a reservoir. This is an isotropic homogeneous reservoir, which is the assumption for most reservoir modeling. And so we're going to use